This video is going to be our end cap to our introduction or quick start to PyTorch. And in this, we're going to basically train a neural network end to end with the real data set and get real predictions. So to start, we just have a bunch of imports, both from Torch core itself, as well as the Torch Vision module, since we're going to be working with an image data set, in this case, FashionMNIST. Even though we're not going to be doing anything with convolutional neural networks, we're not going to be doing anything with diffusion models, even though I imported kind of the utility functions from Hugging Face diffusers. This is to just visualize images in a pretty easy way. And the second bit of this kind of boilerplate is just initializing the accelerator or the device we're using. In my case, we're using my computer's GPU. If you're running this in Google Colab, it might use a CPU unless you're using a GPU machine. If you're running this on a Mac that does have Apple Silicon, this most likely is going to pick up the MPS device or Metal Performance Shaders. So that's just a convenience single line that you can put to make sure that whoever and wherever your code is running, it finds an accelerator if it can use one, and if not, it defaults to the CPU. And the second bit here is the main reason why we're actually using Torch Vision in this video. So the FashionMNIST Dataset comes packaged in the Torch Vision module, and Torch Vision has a bunch of just doing stuff with images in PyTorch kind of functionality. It has data sets, it has pre-trained models, it has transforms to transform your images, augment your data. In this video, we're not getting into convolutional neural networks or anything that's image specific. We're just using multi-layer perceptrons, but I wanted to call it a real data set or an interesting data set instead of synthetic data that we might generate ourselves. And there's two kind of method calls here because these dataset modules inside of Torch Vision give you a training and a test data split usually. So here, the first argument is the folder we want to download our data to if we don't already have it. We specify download true. We do want to download it if we don't already have it. We want the training data set. Here, train equals false gives us the test data set. And the last bit is a transform that we want to apply to every item in this data set. So this basically just converts all of the data into proper tensors that we can manipulate and use with PyTorch. If we look at our shapes, we can see we have 28 by 28 images. So this is identical to the MNIST dataset if you've worked with the MNIST digits. The difference with this is that instead of digits, we actually have a bunch of kind of categories of clothing items. So here we have 60,000 in our training dataset, 10,000 in our testing dataset. And if we want to visualize this, I first kind of showed this cell with 28 by 28. So we can see here, we can make out there's a shoe, a shirt, a dress, a long sleeve shirt, a sneaker, a high heel. But for the sake of this video and making things a little bit easier for folks who might be watching the YouTube video instead of running the code, we can basically resize all of our images. And this again is in the Torch Vision kind of transformation modules. And we can use this make image grid from the diffusers utils. This is really the only function from diffusers we're going to use in this notebook. So don't worry about understanding anything about diffusion models or importing other kind of pipelines or what have you. We're really just using this to visualize our images in a somewhat sane way, where if we were only using Torch Vision, we would kind of have to do this from scratch and kind of manually visualize this and reshape things ourselves. So here, instead of digits, FashionMNIST has clothing items. The nice thing about it is that the both structure of our data, it's 28 by 28, just like the original MNIST, but also our classes or our labels, we have 10. So this is basically a drop-in replacement for any network or code that uses standard MNIST. You can drop in FashionMNIST You don't have to change anything about your network architectures. You don't have to change anything about your classes or your predictions. And the idea behind FashionMNIST is that it's maybe a little bit more interesting, but also harder of a task. So standard MNIST is kind of a solved problem with a dummy kind of tutorial network. You can get basically perfect accuracy or near perfect accuracy on it, which doesn't really make things that interesting. So FashionMNIST is a way to basically make MNIST a little bit harder, more complicated, but also somewhat richer data. For our network, I'm going to paste in kind of a bunch of code here and talk through it line by line instead of writing it out one line at a time, just so you can kind of have the full context of where we're going to end up here. So when you are using Torch or PyTorch and you are using the neural network module of it, to create a new architecture, the kind of convention is to subclass nn.Module, so torch.nn.Module, and this gives you all the functionality, kind of the built-in stuff that makes all these neural network layers and everything work pretty seamlessly. It prints out really interesting stuff. If we run this cell, we can see we actually get printed out all of the neural network layers with all of its arguments. And this comes from the fact that we're subclassing neural network.module. And we're basically calling the initializer on that neural network module before we actually start defining our layers and our functions and everything else. And this bit of code should look familiar if you've seen maybe Keras or TensorFlow layers. This is kind of evolved into one of the standard abstraction interfaces for defining network architectures. And here we basically have a nn.sequential class object. And this basically signals to PyTorch that we're going to pass the inputs through a layer, get outputs. Those outputs become the inputs of the next layer in our sequential, and so forth, all the way through until we get to the end. Now, you could imagine you want to define an architecture where you maybe fork off into two different paths. In that case, you wouldn't be using sequential. But for our case, a simple multi-layer perceptron, every layer feeds its output as input to the next layer. Sequential is just a convenient and really nice way to encapsulate all this. Inside of sequential, we're defining layers that are basically, in this case, just linear layers, which correspond to fully connected layers. And the arguments to .linear or neural network.linear are basically the dimensions of the inputs first and then the outputs second. So since these are fully connected linear layers, we essentially need to flatten our input data, which is what this flatten module is going to do here. And this essentially just stretches out these images. And instead of passing them as a 28 by 28 matrix, we just get a single long 28 times 28 length vector. So this is just collapsing that second dimension. The second bit of this linear layer is basically saying we're going from an input of 28 times 28 into 512 numbers or values. The next bit goes from 512 to 1024, 1024 to 512, 512 to 10. And the important thing is the output, kind of final output, and the initial input. So as long as you have the initial input set to the dimensions of your data, as long as you have the final output set to the kind of dimensions of your labels, everything that happens in the middle here, you can always match up the layers to make any sort of dimensions work. So here we could have changed 512 to 1 if we really wanted to. And since we changed 1 in both places, this isn't really going to create any issues for us. If we want to change this 1024 to an arbitrary 7, we can change the output of this linear layer to 7 and the input of the following layer to the same value because we're using this sequential module. And I'm going to just undo those. And the other bit is that for a neural network, you need a non-linearity. You need some sort of function to basically run on just these linear layers. And in this case, we're using the ReLU, which is kind of, if you don't have a better non-linearity to use, ReLU is kind of the best default. It works pretty well across a wide range of use cases, and there are definitely more sophisticated activation functions, but ReLU is kind of one of the workhorses of neural networks, and especially kind of just simple multi-layer perceptrons. The second bit here, so this is all in the initialization of our class. All of this .init gets called when we do MLP parentheses, close parentheses. This creates a new object. It initializes all these layers, and it adds them as just attributes. In this case, self.flatten and self.layers. So to actually run these, the convention of nn.Module is that we define a forward method that takes as input, in this case, just a single data element or a batch of data elements. We're first calling .flatten on it, and then we're passing that flattened data to our layers and returning that. So here we can see our multi-layer perceptron. We initialize it when we print it out. It shows our layers and kind of the attributes we've attached to it. And to actually run the forward function, you basically initialize your network and then you call your network like a function, and that runs the forward method for you. But we'll see that in the full kind of training loop in just a second. So we run this, we have our MLP, and this is kind of one half of training a neural network, is defining the network architecture itself. And I wouldn't worry too much about a lot of these dimensions. I've picked somewhat arbitrarily. You can think of them as hyperparameters, things that you're not learning when you're training on your data, but you're basically just setting them based on your own prior knowledge about what might work for your given problem or your given data set, or you're doing some cross-validation where you're finding the optimal set of hyperparameters. But don't stress too much about Y512, Y1024, Y512. Again, the output is really what matters. So the final output of 10 and the initial input of 28 times 28. To actually train this network, we're going to need a few more modules or functions from Torch. The first one is we're going to need a loss function here, which is cross entropy loss, and then as well as an optimizer, which we're using stochastic gradient descent, which is just going to be our way of updating the weights of our neural network. So here we're creating our MLP. As I showed before, we call it like we're initializing a new class. We're putting our multi-layer perceptron on our device. And this essentially puts all of the weight tensors, all of the internal kind of functionality of our layers on a given device, so that when we're actually training it, it actually does use something like the GPU. Cross entropy loss is just one of these built-in loss functions. There's a bunch of them in NN, the neural network module, and cross entropy loss, basically just choosing it because this is what works for a classification task. If we're doing a regression task, we're going to want to do something like mean squared error. And again, just like everything in PyTorch, there's a plethora of loss functions that you can choose based on your problem, your data, some prior knowledge that you might have. But again, just like the ReLU, cross entropy loss is kind of the standard classification loss for a multi-layer perceptron. We initialize our optimizer, our stochastic gradient descent here. So we pass in the trainable parameters of the neural network, and these are basically the things that we're going to update in this backwards pass or this optimization loop. We set a learning rate. Again, this is a hyperparameter. This is the learning rate that works well given this architecture and given this data set. This is something that, again, there's kind of ranges of sensible values to use. A lot of it's just experimentation and find out what works. And we're passing in a momentum argument to basically help this stochastic gradient descent learn a little bit more efficiently. Now, getting to the actual training loop, one thing when doing something with kind of mini batches is that you have this idea of what's typically called an epoch, which is how many times do I want to go through my entire data set? So every batch goes through 64 elements at a time, but we want to go through our entire data set of 60,000 elements 5 times. So that's where this for epoch in range comes from. And then for each epoch, this is essentially what we're doing for each batch. So to go through and iterate through our data set, this data loader turns our FashionMNIST dataset into essentially an iterable that we can just use a normal for loop for. And the data loader initializer, we basically need to specify a batch size, whether or not we want to actually shuffle our data. And this, you can think of it as almost a random seed. So if we wanted this to be predictably shuffled in the same way every time, we would set a seed on this generator, and that'll ensure a little bit more reproducibility. So here we're just iterating through, and enumerate is just wrapping our data loader. So now we get basically the index as well as the data. The data, remember, is our input images, but also our labels. We're putting both of these on our GPU since our device is already on the GPU and we want to accelerate this learning. And now comes kind of the meat of the training loop. So I went through all of this fairly quickly because it is a little boilerplate-y. We're just getting our data ready to actually do our learning. But the actual learning, we first are going to need to zero out any of the existing gradients. If you've seen my last video, when you are doing backpropagation in a for loop, you are accumulating the gradients basically every time you run dot backwards. So for this to actually properly update the weights of our neural network, we need to zero out any of the existing gradients before we actually run the next backwards pass for the next mini batch or the next iteration. The kind of standard convention, what I internally think of in my head, is the optimization process for training a network is basically forwards, backwards, optimize. So here we run the forwards pass of our neural network by passing our inputs to basically our network that we call as a function. So this is going to give us our predictions. With those predictions, we're computing how well they actually predicted our labels. So our loss function here, cross entropy loss, this is basically a measure of how well our network is learning. What is the loss that we're going to backpropagate across? So with this loss, we're going to call the backwards function. And I went in a little bit more detail in my last video about some of the internals of working with backpropagation in PyTorch, so I'm not going to go through all of that here, but just know that dot backwards updates gradients in place. So unlike the loss function, which actually returns the loss, dot backwards goes through this whole computational graph that ends with loss and updates all the gradients of everything that we might need gradients for. And the last bit that actually updates the weights of our neural network is this optimizer.step. So optimizer.step uses the stochastic gradient descent algorithm to update all of these net.parameters, which are our weights and biases of our neural network. And the last bit of what we're gonna maybe want to do is visualize our progress. So here, every 100 mini batches, we're basically just printing out our running loss, and we're keeping track of our loss here, basically for each epoch. So now this is the grand training loop. It might look intimidating like a lot of code, but if you've done non-modern deep learning, you know how much worse this can get if you really have to specify each one of these things like stochastic gradient descent by hand, parameters by hand, cross entropy loss by hand, iterate through mini batches by hand. So this is kind of a nice in-between of needing to specify everything manually and kind of tweaking every little bit, and maybe something that's a little bit more or too high level. Something like Keras, which has much more of a scikit-learn like API, where you basically just pass in your data to a function train and it trains everything for you. This gives you some control, but makes it so you don't need to specify every single kind of operation you're performing. Now, if we run this, I actually had my printing out the loss outside of my mini batches. So if we run this, we should see the loss getting printed out here. As long as the loss is predictably going down, then our network is actually learning. So the magnitude of the loss itself isn't as important as the fact that the loss is going down. It's starting off at 2.288. And we can see here as we train our mini batches, as we go through our epochs, we're kind of bottoming out around 0.5. We might be able to train this a little bit more. You could train this for 10 epochs. How well you're actually going to be performing on the test data set really depends on whether or not you're using some sort of regularization in your network. You don't want to overfit, so that's why I'm only really training for 5 epochs here. I'm going to create a test data loader with our test data set here so that we can actually iterate through our test data and get a sense of how well we actually learned the classes of our data set. And what we have to basically compute our test error is somewhat boilerplatey, but I will highlight the PyTorch specific things. So the first bit is this net.eval. So we're not actually using any regularization layers, things like dropout or batch normalization. But if we were, .eval basically signals to the network to basically set it to inference mode. So .eval isn't really important for our given architecture, but most likely you're going to use an architecture with some regularization, some batch norm or dropout, or you're using someone else's architecture, an architecture from the Torch Vision pre-trained models. And it's always just good habit or practice to call .eval. Here we have our test loss and our number of correct. And the second bit of kind of PyTorch specific stuff is using this torch.nograd. And if you saw the last video, this is the same as basically calling .detach on all of the tensors or things within this context statement. And torch.nograd just signals to PyTorch, we're done computing gradients. You don't need to store gradient information in the computational graph, since we're just performing inference at test time here. Everything else in this little block is the same as basically what we saw in the training code. We're just updating our losses and how many predictions we got correct in each one of these mini batches. We then normalize these values based on the total number of data elements we have, and we print it out. And here we can see that even with this kind of, call it toy neural network, on a somewhat interesting and kind of complicated data set, the FashionMNIST dataset, we got an accuracy of 81.6%, which may not sound good, but remember there's 10 classes. So if we were randomly predicting a class, we would have an accuracy of just 10%. So an accuracy of 81% on these complex images is actually somewhat impressive, especially since the network we're using is somewhat simple or rudimentary. This should show you just the power of deep learning and neural networks in general. So with that, that's kind of our end cap of the PyTorch, call it 101 series, the playlist. If you have any specific PyTorch errors, bugs, questions, feel free to put it in the comments. If you do have something, a more specific topic you want me to cover on something in PyTorch or its modules or its extended ecosystem, also put that in the comments. And hopefully you feel comfortable now with this base PyTorch knowledge to explore other arguably much more interesting libraries like Hugging Face transformers and diffusers, or any of the other kind of libraries built on top of PyTorch that are either specific to a domain or specific to something like reinforcement learning or probabilistic programming. PyTorch is really this great base.